Welcome to JE Maths Unlocked. Today, we're going to explore a classic idea in combinatorics: how to distribute n identical balls into r distinct boxes. Imagine this: you have n identical balls and r distinct boxes, each uniquely labeled. The question is, in how many ways can we place these identical balls into the distinct boxes? But here's the twist: we need to consider two important cases. Case 1, empty boxes are allowed. Case 2, empty boxes are not allowed. Let's begin with the first one. Empty boxes are allowed. We'll first take a specific case to build our understanding, and then we'll generalize the result. Consider this scenario. You have 7 identical balls lying on the floor, and you want to place them into 3 distinct boxes. Let's call them Box A, Box B, and Box C. Now here's the key idea. Since the balls are identical, what matters is how many balls each box gets, not which balls go where. So how do we count the number of ways to do this? Let me show you a little trick. Introduce 2 partition lines. Think of these lines as dividers that separate the balls into 3 groups. 1 for each box. Now, imagine placing these 2 dividers somewhere among the 7 balls. Each unique placement of the dividers corresponds to one possible distribution of balls across the 3 boxes. This arrangement means Box A gets 2 balls, Box B gets 4 balls, Box C gets 1 ball. Now move around these 2 partitions to get different distributions. Another arrangement might be like this, which means 0, 3, and 4 balls are like this, which means 3, 0, and 4 balls, and so on. So, how many total such arrangements are possible? It's just total number of arrangement of 7 identical balls and 2 identical partitions, which is factorial 9 upon factorial 7 into factorial 2. Further, we can write it as 9c2 equals to 36. Let's now generalize this beautiful idea. If you have n identical balls and r distinct boxes, then the number of ways to distribute them is factorial n plus r minus 1 divided by r minus 1 factorial into n factorial, which can also be written as n plus r minus 1 cr minus 1. This is often called the stars and bars theorem, one of the most elegant results in elementary combinatorics. It transforms a complex-looking distribution problem into a simple counting formula. Now let's consider this equation and we're looking for non-negative integer solution. You might wonder, why does distributing identical balls into boxes become a problem of non-negative integer solutions? Here's the connection. Let's say you have n identical balls in r distinct boxes, labeled A, B, C, and so on. Let x1 be the number of balls in box A, x2 in box B, and so on up to xr in the rth box. Since you're placing n balls in total, you must have x1 plus x2 plus x3 plus till up to xr equals n. And because a box can hold 0 or more balls, each xi is a non-negative integer. So, finding the number of ways to distribute n identical balls into r distinct boxes, with empty boxes allowed, is the same as finding the number of non-negative integer solutions to this equation. And the total number of such solutions is n plus r minus 1 cr minus 1. This is a classic stars and bars problem in combinatorics. Now let's move to the second case. What if no box is allowed to remain empty? That is, every box must receive at least 1 ball. Let's dive into that. If you have n identical balls in r distinct boxes, and each box must get at least 1 ball, then here's what you do. Now here's the trick. First, assign 1 ball per box. That uses up r number of balls. Now, you're left with n minus r balls to distribute without restriction. We can use the case 1 here. So the total number of ways, n minus r plus r minus 1 cr minus 1, which simplifies to n minus 1 cr minus 1. Let's now take a look at this equation. Suppose we're looking for positive integer solutions to this equation. That means each xi is greater than equal to 1. This is directly connected to our second case, distributing n identical balls into r distinct boxes, where no box is left empty. Because every solution to this equation represents one way of placing balls so that each box gets at least 1 ball. And the number of such solutions is given by the elegant formula, n minus 1 cr minus 1. This isn't just a formula. It's a bridge between algebraic equations and real-world distribution problems. So next time you see a problem asking for positive integer solutions to a sum, remember, you're really solving a distribution puzzle. For more such clear and intuitive explanations, subscribe to this channel, JE Maths Unlocked, where math isn't just solved, it's understood. See you in the next one.